All right, so next we're going to take a look at a fairly lengthy example, so bear with me, and if you need to pause the video in the middle just to take a quick break, that's fine. But we are going to look at a probability distribution function, or in statistics known as a PDF. What this is, by definition, is a table where the probabilities, let me try, where the probabilities of each outcome, which we denote with a capital X, in the sample space are given. Okay, so it's basically just a table where the probabilities of every outcome is written down. Okay, now a couple of things to keep in mind. Okay, the probability of any single one of those events has to be between 0 and 1. Okay, that's our definition of probability. And the sum of the probabilities of all of the events, okay, all of the outcomes, have to be 1. They have to add up to 100% of the time. Okay, now again, I know that that can look a little scary. Got some big math terms in there. Let me break it down for you. Okay, try to make it easy as possible for you to understand it. So here is an example. Okay, a Wendy's manager did a study and made a probability distribution for the number of people, X, waiting in line during lunch. Okay, so the first thing I want you to realize here is that this value, all of those X's from 0 to 9, are the number of people in line. Okay, number of people in line. Okay, that's how many people are waiting in line. Then when you see P of X, this is the probability of that many people being in line. Okay, so when you see X is 0, that means there was nobody waiting in line, a probability of 0.011, or about 1.1% of the time they had nobody waiting in line during lunch. Okay, when you go to the next one, there was one person waiting in line. Again, I'm going to say that as a percentage, about 3.5% of the time. Okay, so just take some time to really focus on what that means, because this table, based on personal experience and this experience of my students, can be really confusing unless you take the time to break it down and understand what those things mean. Okay, so the first thing we're going to do is fill in the probability that X equals 4. Okay, that would make this a probability distribution function. So this is saying find the probability that there are 4 people waiting in line. Okay, remember that's what X means, number of people waiting in line. So when we look at all of those probabilities listed across the second row of the table, remember that they have to add up to 1. Okay, the sum of the probabilities of all of those X values have to equal 1. So if you add up what's there, we will find that the probability that there are 4 people waiting in line has to be 0.25, because those other values add up to 0.75. Okay, so the way you would say this is the probability that X is 4 is equal to 0.25. Or what I prefer to do, instead of saying X all the time, I keep context. The probability there are 4 people waiting in line is 0.25. Okay. All right, so let's look a little bit further here. Okay, what is the probability there are 8 people waiting in line for lunch? Interpret the probability. Okay, so what are we looking for? We're looking for the probability that there are 8 people waiting in line, so that X is 8. And when you go to the table and look down next to the last column, okay, you find that the probability is 0.063. Okay, we need to interpret this probability. So again, finding that number on the table is not a difficult question, okay? What I need you to really understand is what in the world does it mean? Now, I'm going to write this answer as a percentage form because that's how we speak when we talk to each other. We don't usually talk about the decimal form. So I would say 6.3% of the time there are 8 people waiting in line at Wendy's during lunch. Okay. Then there's a follow-up question to that. Notice it says, would it be unusual to walk into Wendy's and see 8 people waiting in line? Now, if you go back a couple of pages in our notes, we talked about some definitions of unusual, okay? We have the one about standard deviation, the one about interquartile range, and we added a new one in chapter 4 that said less than 5% of the time means unusual, okay? So in this case, since the probability that there are 8 people waiting in line is greater than 0.05%, this is not unusual. Okay, so make sure you're answering all the parts of the question. There were 3 things there that we had to do. All right, looking at the next part, part C, find the probability that X is greater than or equal to 6, and then interpret the probability. So X is greater than or equal to 6 means we want to add the probabilities of there being 6 or more customers waiting in line. So 6 customers is 0.132, 7 customers, 0.063, same for 8 customers, and 9 customers, 0.035, for a total of 0.293. Okay, and again, interpret the probability. Okay, so there will be 6 or more people waiting in line 29.3% of the time. Okay, continuing on to question D. Find the probability that at most 2 people are waiting in line. Now this is one of those we have to understand what at most 2 means, okay? At most 2 means a maximum of 2 people, okay? So we want to find the probability that X is less than or equal to 2, that there are 2 or fewer people waiting in line. So we want to add the probability that no one is waiting, 0.011, plus 1 person, 0.035, plus 2 people, 0.089, for a grand total of 0.135.